OGL project, the optical gravitational lensing experiment. I must say that this name and this acronym was coined by George Preston 30 years ago. And George was also the member of the original OGL team. I can say that George was one of the founding fathers of the OGL project. And my talk will be devoted to the small part of the OGL research, the Cepheids, RLI stars, a little bit about delta Scuti stars, in other words, classical pulsators in the Milky Way only. These points here show the positions of the classical Cepheids detected by the OGL project above our telescope. But first, let me tell you something, very briefly present you the history of the OGL project. Unfortunately, there is no photo with all members of this OGL1 team, so I have to find the pictures from the internet of these members of the project. At the beginning, it was the Polish-American project. However, 6.5 of these members were Polish out of 8 members of the OGL1 team. OGL started almost exactly 30 years ago in April 1992. The first phase of the OGL project was carried out with this 1-meter swope telescope at Las Campanas Observatory. Then in 1996, the dedicated 1.3-meter Warsaw telescope was built, and in January 1997, the OGL2 project started. Then in 2001, the Warsaw telescope was equipped with this 8-chip CCD mosaic camera designed and built by Andrzej Udalski, our leader, our boss. And then the third phase of the OGL project started. And finally, in 2010, Andrzej built a new 32-chip CCD camera, and the OGL4 project started. Unfortunately, in 2020, the telescope was closed due to the COVID pandemic, and it's still closed. We plan to start OGL5 project. Among others, we plan to change our filters, but we still don't know when it will happen. Here, Andrzej Udalski is constructing the camera in the clean room at Las Campanas. Some more details about the project. Well, the field of view of the camera is 1.4 square degrees. We use standard V and I band filters from the Johnson-Cousins photometric system. So our observations are well suited for any calibration purposes, for comparing our observations with historical observations. And the precision of the photometry as well. The OGL photometry is one of the most precise photometry compared to other ground-based large-scale sky surveys. We observe the densest regions of the sky visible from Las Campanas, the galactic bulge, galactic disk, and the Magellanic clouds. In total, 3,600 square degrees. We regularly observe about 2 billion stars and 10 to 12, 1 trillion. This is the number of individual photometric measurements stored in the OGL databases. And as far as I know, this is one of the largest, if not the largest, photometric database in the world. And this huge database was a basis of many discoveries, among other, one of the largest, if not the largest, at least until Gaia is not published its catalog of variable stars. We call this catalog the OGL collection of variable stars. This is a sub-project of the OGL project with the main goal of detecting all variable stars and classify them. that can be detected and classified. This table shows how many variable stars of different types have been included in this collection so far. We already exceeded 1 million objects, and my talk will be devoted to present classical pulsating stars in the Milky Way. This is the web page of an example star, so everyone can find here the basic information, basic parameters of a given star, its time series photometry, light curve, finding chart. It's a very user-friendly system, so I encourage you to use this data. Here is the picture of Yuri Belecki showing the Milky Way above the Ogle telescope, the galactic bulge here. I want to show you the progress that has been made thanks to the Ogle during the Ogle project. Here is again the galactic bulge, and these tiny squares here are Ogle-1 fields. About 1.5 square degrees, and about 2 million stars were regularly observed during the Ogle-1 project. Then these are Ogle-2 fields, about 11 square degrees and 36 million stars monitored. Ogle-3 coverage, 300 million stars were observed during this project. And finally, the Ogle-4 fields covering practically the entire galactic bulge. The observations, the time span of the observations in different fields are very different. In some cases, it's nearly 30 years. In some cases, it's just a few years. Also, the frequency of the observations are different in different fields. In the next slide, I show you this region. This is just the 20 per 20 degrees in the sky, because I want to show you the progress that has been made thanks to the Ogle observations. Here, this is the same region in the center of the galaxy, and these points here show the positions of RLI stars known before Ogle started, about 30 years ago. More than 1,000 RLI stars, very heterogeneously distributed in this area, were known. And these are positions of RLI stars from the Ogle collection of variable stars, more than 50,000 objects. Well, this gap here is, of course, caused by huge, enormous interstellar extinction toward the plane of our galaxy. This is inaccessible region for the optical observations, but generally, I think it's well visible, this progress. So here I present you the number of different types of classical pulsators included in our collection. This is the largest set of classical pulsating stars in one collection, in one catalog. The light curves are quite similar, but we are astronomers. We easily can distinguish between different types of classical pulsators. No, I'm joking. A few years ago, only several anomalous cepheids were known in our galaxy because it was a problem to distinguish between anomalous cepheids and classical cepheids, or anomalous cepheids and RLI stars. But we found the solution to this problem. We used our huge catalog of classical cepheids in the Magellanic Cloud, in particular in the Large Magellanic Cloud. Here is easier to classify stars because we have the different period luminosity relations. Here are the anomalous cepheids, and we use the parameters of the Fourier decomposition of the light curves. We put these Fourier parameters, especially phi-2,1 and phi-3,1, against the period, and it turns out that different types of classical pulsators could be easily distinguished in this plane, these planes. here, and we use this method to find quite a large number of anomalous Cepheids in our galaxy. It works for fundamental mode pulsators and works fine for first overtone pulsators. Let's go to the results. Let's start with classical Cepheids. So just 4 years ago, only 900 classical Cepheids were known in our galaxy. We increased this number to 2,500 objects. These yellow points show the position of all classical Cepheids, those that were identified in our database. These blue points are classical Cepheids detected in other databases from other projects. However, some of them were classified also by us, or the classification was verified by our astronomers. And we determined distances to each individual Cepheid using their mid-infrared observations and mid-infrared period luminosity relations. And this is the result. This is the face-on view of our galaxy. Here is the sun and the galactic center. And these blue points are classical Cepheids identified by OGU. Other colors indicate other catalogs. And I think it's well visible that we significantly increase the number of known classical Cepheids, especially for larger distances from sun. And we use these Cepheids to prepare the most accurate 3D map of our galaxy, of the disk of our galaxy. Let's look again to this map, this sky map, because I want to draw your attention to these stars here, which are mostly located below the galactic equator. But here, most of them are located above the galactic plane. This is not a coincidence. This is caused by the disk warp. The disk is twisted, like in this galaxy. Maybe in our galaxy is more, this effect is more subtle, however, clearly visible. This animation shows this effect, how the galactic disk is twisted. The reason of this shape of the galactic disk is not clear. Probably the interactions with the Magellanic clouds could be the reason why the galaxy disk is warped. What's more, this is again face-on view of our galaxy with our Cepheids, but this time we use the classical Cepheids to perform the age tomography of our galaxy, because classical Cepheids are amazing stars that allow us not only to determine their distances but also their ages, thanks to the period age relation. And here different colors of the points show different ages of Cepheids. The youngest one are here, these blue points. The red points are the oldest one, and the gradient is well visible. The youngest one are located closer to the galactic center, the oldest one in the outer regions. Moreover, these overdensities here are composed of Cepheids with the same age, which made us to perform a simple simulation. We injected star formation episodes in given spiral arms in given range of times, and we evolved these stars, assuming velocity dispersion, assuming differential rotation of the star, and finally we obtained in our simulation very similar age distribution that is observed. This is our simulation. Sorry, that is in Polish. And here in a moment it will be the observed distribution of Cepheids, and this is the simulation. And finally, the last exercise, we obtained the most accurate rotation curve of our galaxy. These distances were taken from the infrared period luminosity relations, and the kinematics, radial velocities and proper motions were taken from Gaia, and this is the result, the most accurate, especially in this larger distant galactocentric distances rotation curve of our Milky Way. I have little time, so rest of my talk will be devoted to unique objects, very rare objects or previously unknown, like this one, the first known classical Cepheids with eclipses in the Milky Way. A few such objects, nearly 10 such objects are known in the Magellanic Clouds, and this is the first Cepheid which shows additional eclipsing variations in our galaxy. However, we are not sure if this is this Cepheid is a member of this binary system or these are unrelated stars, eclipsing binary and classical Cepheid at the same line of sight. It should be checked spectroscopically. We found several such stars among type 2 Cepheids and several dozen such stars among delta Scuti stars. As Gergely said, we don't know any RLI star with eclipses so far. Another interesting object, RLI star that switched its pulsation mode. It was, and this is the same star, the same light curves of the same star. It was a RRD star, double mode RRD star, and it became a single mode RRAB star. We found
what time scale?
In very short time scale, just in a few months, several months. Periods are nearly the same, not exactly the same. Periods change a little bit, and completely amplitude of the fundamental mode was increased, and completely the first overtone and pulsations were ceased. Yeah. But so we have, it was the first time when we have opportunity to observe this effect in 3 such objects, as I remember. And very interesting new objects were found among multi-mode classical pulsators, double and triple mode pulsating stars. This is the Petersen diagram, period ratio versus the longer period. Different colors show different types of classical pulsators. These are, of course, fundamental and first overtone pulsating stars, first and second overtone pulsators. And we have several second and third overtone pulsators, triple and double mode pulsating stars. Let's start with RLI stars, because we identified a new subtype of double mode RLI stars. We called it anomalous RRD stars. These are these yellow points here in the Petersen diagram. They, as you can see, they avoid the sequence for classical RRD stars, these black points. But this is not the only difference between these 2 types of double mode RLI stars. Anomalous RRD stars have different amplitude ratios. Usually the fundamental mode is dominating. Different light curve shapes, and they usually show Blaschko effect. We found the first type 2 Cepheids, 5 such objects, double mode type 2 Cepheids, because just a few years ago, all type 2 Cepheids were thought to be pure fundamental mode pulsators. We found the first one, type 2 Cepheids. We found the first one, first single mode, first overtone type 2 Cepheids. In the Large Magellanic Cloud, 2 such objects. They are located close to the theoretical line for first overtone type 2 Cepheids, and 3 similar light curves were found in our galaxy. And finally, we found the first one, 2 points, but belonging to one object. because this is the triple mode pulsator. The first one, multi-mode anomalous Cepheid, and these are the disentangled free light curves of the same star of 3 modes of the star. We are convinced that this is an anomalous Cepheid because the Fourier parameters are located exactly on the sequence for anomalous Cepheids here. And that's it. These are my conclusions. Sorry.
Thank you. Time for a couple of questions.
You didn't discuss or talk about the distinction between identification of RR type C variables and delta Scuti stars. How do you distinguish between them?
Yeah, using the Fourier parameters, I didn't show you the Fourier parameters. Generally, it's a bigger problem for first overtone pulsators because the distinction is not so clear as in fundamental mode pulsators. But most of the delta Scuti stars have periods much below 0.2,
So
much shorter.
Like 0.2 of a day or something like that?
Yeah, we have some delta Scuti stars above 0.2 of the day, and we generally use the Fourier parameters. They are slightly different than the RRC stars, but generally it's not a big problem because the overlap is not large, I would say.
Beautiful map of the Cepheids in the disk. Those distances, do they come from a PL relation or from Gaia?
Yeah, the distances come from the PL relations, but not in the optical bands, but in the mid-infrared bands, from the WISE telescope and from the Spitzer telescope. And
so, how big of a volume will Gaia be able to do as well or better in terms of parallaxes for those stars?
Really comparable, but when this paper was written in 2018, the Gaia parallaxes, they were only the Gaia data release 2, yeah. And the parallaxes were not accurate enough.
Will DR3 help it a little bit?
Probably, yeah. DR3 will be in a few days.
One more question. One more.
Another beautiful image of the ages of the Cepheids. There are no selection tests that might cause that. I mean, I'm not expecting to see younger stars towards the center and older stars towards the outside. That's just not my, I work on much older stars. So you think it's a real effect that
it seems so, because I don't think the younger stars have longer periods and are brighter. Yeah. So if we see
so you should see them everywhere.
Yeah, I don't think there is a.
Model that you used and explained was just simply an increasing star formation rate towards the center of time.
Older stars wander. The velocity dispersion tends to wipe out spiral structures. Is that right?
I think it could be as simple as that. Yeah. Oh, but it was like 10 kiloparsecs.
The velocity dispersion in the field, if we were talking about field stars, is what, 10 kilometers per second?
To go that far.
Oh, no, maybe not. I just tried.
Yeah. No.
We have one more online question, Horace.
Yes, very interesting. I was wondering if you can say anything about the stability of the amplitudes in the multi-mode RLR stars. Do the amplitudes of the different modes stay pretty constant over time?
Oh, we have tens of thousands of objects, and there are all types of behaviors among other stars. Also, there are stars with very stable light curves. And we have stars with various variations, various changes of the light. Amplitudes can change, and the mean magnitudes can change, and the periods are changing in some stars.
Mhm.
I don't know if I answered your question.
Oh, I can check with you at some other time. I was just thinking about the double mode RLRs in particular.
Double mode. Okay, sorry. So you ask for Blaschko effect?
Well, or whether just the ratio of the first amplitude, the first overtone to the fundamental mode changes with time in a typical double mode RLRA.
I didn't check it, yeah, precisely. So I don't know how to answer. Generally, it's stable, but probably it's possible to find also stars with change this amplitude ratio.
Thank you.
We need to move on now. Let's thank Igor again. Thanks.
Thank you.